Our third and final talk today is from Professor Mainak Majumder. Mainak is a professor in the Department of Mechanical and Aerospace Engineering here at Monash University. He is the director of the AM2D Research Hub and is an associate director of the Monash Energy Institute. Mainak's research interests include energy-efficient water filtration systems and energy storage systems. Mainak, I welcome you to the podium for your talk, From Batch to Flow-Based Methods for Production and Modification of 2D Materials.
Hold on, connected it. All good?
All good.
All right. I think I got this. All right, guys, did you use the mic? Oh, all right. I guess, so my talk, you will be focused on batch to flow-based methods for production and modification of 2D materials. This is kind of a really new area we are venturing on, especially with the new hub. One of our goals is to be able to produce these 2D materials in a scale so the industry can adapt it or make a judgment of the usefulness of this material. So that is the reason we have slowly tried to come to this area. Now, sorry. All right, so I guess my talk, we will kind of talk about batch versus flow, what are the advantages, disadvantages, as well as, why do we choose flow processing approaches. Then we will discuss some examples from literature on nanomaterials. The reason we want to talk about nanomaterials is because flow chemistry has been applied to, specialty chemicals for hundreds of years. It's nothing new. But nanomaterials is something different. And people are beginning to realize that the quality of nanomaterials, the reliability of nanomaterials is a big question. And we will look at literature and see how these are produced by flow chemistry. Now, then we will talk about not two-dimensional materials as such. We will talk about bulk 2D materials, which is a big part of the hub. Because if you look at the commercialization activities around the globe, the majority of them are looking at bulk 2D materials. I'll give some examples from our lab on electroflow chemistry for synthesis of 2D materials, and then photochemical. This is the work of Wanqing for scalable production of holey graphene oxide materials. And then I kind of demonstrate our core competencies, some selected recent publications, right? Now, what is batch versus flow? I guess you move a bulk material with a group of reagents through individual predetermined sequential steps, whereas in flow, you actually move a unit of material from one step to the other. That means that the batch is an intermittent process, and in a flow process is there is no breaks in time, sequence, or extent. So a typical batch process is like this. You have a reactor, you put in reagents, and you get a product. Whereas in a flow, you have got the reagents, it flows through a column or a tube or whatever it is, a reaction happens, and you get a product. Now, what are the advantages? I think this could be interesting for Kurosh also, is that, there is a much rapid heat and mass transfer, larger surface area in the reactors help you to achieve this high mass and heat transfer. It's safer and less waste is produced, and cost of space is reduced, transportation of chemicals are reduced, so your cost benefits are quite large, actually. And then the other thing which we have realized is that the rapid scale-up is possible without going through a large process development steps. Of course, the disadvantages we have is that it's a new approach, and then you've got a wide range of reactors to choose from, so the knowledge base has to be created. I guess there are some challenges, clogging of the reactors and stuff like that, but this is not something which is unsurmountable. I want to mention here that flow reactor is not a panacea of everything, but they represent an excellent complement to traditional batch reactors. Now, this is something already in the literature. We gather it and put it here. So, for example, if a process is in a batch, acceptable yield, reaction time, and scale, If it goes to equilibrium reaction and there is a reasonable low market demand, then you would probably do batch process. However, if the process can benefit from moderate pressure and temperature, if you need a fast heat up, fast mixing, and then if you have safety issues, you have got high energy cost, catalyst deactivation, and there is a big market demand, as well as if the reactions are driven by photochemistry or electrochemistry, then flow is probably an approach which you should consider. Now, some examples. Nanomaterial synthesis by flow chemistry. This is a work published in JACS, MOFs. We have a pretty big group here at Monash working on MOFs. And typically, when you're synthesizing MOFs by hydrothermal, it takes several days and hours. Sorry, several hours or days, okay? Now, this work showed that if you're able to do the synthesis in a flow reactor, you can do this in about 5 to 35 minutes. Very, very fast reactions. Quite useful, actually, to scale up. Another example is silver nanoparticle synthesis. Here, they've used a microwave to heat up the liquid. You could use a droplet, etc., whatever it is. But the important point is that there is a much better mixing, fast mass transfer happening in this reactor. So it's a flow-through reactor with a microwave. And what I want to point out here is in a batch, you need 390 watt energy requirement, and at a flow, you reduce it by a factor of 2 or 3. So that's quite exciting, actually. The other example I have here is a photochemical synthesis where they have prepared platinum, palladium, and etc. nanoparticles, and you can see an increase in 300 times in reaction rates. And also the advantage is that it gives a narrow distribution of particles, which are quite exciting in terms of applications. So if I look at bulk-2D materials, essentially you're looking at synthesizing them from mineral ores, exfoliating them, bulk materials. So I tried to find out these methods and how they can attain sustainability goals in United Nations sustainability goals. And we kind of started to build this table. And if I look at the unit processes, you have mechanical cleavage, the way people found that out from or discovered graphene in Manchester, and then coming to more chemical and solvent exfoliation, electrochemical exfoliation. Then the modification, you look at chemical, light matter interaction, electrochemical, plasma, electron beam. So we tried to find out, how do they actually meet all these criteria: yield, safety, reaction time, energy efficiency, cost, and scalability. Obviously, mechanical cleavage, the scalability is low. That means we are not looking at using this kind of approaches for bulk materials. Chemical exfoliation, there is a problem from safety. If you're making graphene oxide synthesis, it turns out that some of the steps associated with graphene oxide, especially the oxidation step, could be quite challenging in terms of safety. Yet, that is what is the preferred way of making graphene materials. So I guess this kind of gives us an idea that not everything is ideal in the world of graphene as we are trying to scale up materials. Oh, sorry. So there have been advances made by a few companies around the world. And this is an example of a reactor called Taylor vortex reactor, which essentially has got co-rotating cylinder. So this cylinder rotates, the other one remains fixed, and you generate vortices, okay? And the amount of shear you can generate in these reactors are quite large. And, there is fluid vortices which help mixing, etc., etc. And this is a really good advance made in the reactor design. So I'm going to show you some examples of using these kind of reactors in making reasonably large-scale 2D materials from graphite or the minerals. So this is a paper published in RSC Advances, which look at exfoliation of graphene materials in a solvent. And then again, people have used the same kind of technique to use molybdenum disulfide to convert into flakes of molybdenum disulfide, MOS2 flakes. They've reached reasonably high concentration of these materials. So technologically, it is possible to use reactors, flow reactors, to synthesize this type of 2D materials. And it is relatively new research field, but has great potential to be used in large scale. I'll talk about some of the innovations we are thinking about in this technology. Products are a function of temperature, time, rotation speed, etc., and a wide number of solvents can be chosen. So there is one of the methods to make graphene from graphite is electrochemical exfoliation. It turns out that one of the companies in Western Australia, First Graphene, they actually manufacture graphene by electrochemical exfoliation, which typically they use anodic potentials and you break it up, you exfoliate the graphite into small flakes. But the reaction is usually rapid and you need a large potential, 5 to 10 volts. What it ends up is essentially you split water and then you have oxidized graphene species, all right? And also when they are doing this method, it turns out that the graphite electrodes mechanically break and you end up with a product which has got thick graphite particles as well as graphene. Okay, so not the most ideal of methods, but if you characterize the product from those companies, you will find that it has mostly, graphite flakes and particles. All right. So to overcome this, we started to think about can we use both shear forces as well as electrochemistry, and we found out that by using shear forces plus electrochemistry, we can actually produce graphene at quite a low potential, about 1 volt, compared to 5 to 10 volts. So this was a reasonably old work in 2016. We were able to produce very large graphene flakes, less defective graphene, single, bilayer, trilayer graphene, where we imposed both shear forces and electrical potential. And also it has got much less oxidative species. So there are advantages of this approach. Now, I guess there is an advantage of translating batch electrochemistry to continuous flow conditions. The advantages of electrochemistry are that you have got reduced waste, etc. We have got but there are issues with heat transfer or insufficient mass transfer in this kind of electrochemistry approaches. So I want to point out to the area of flow chemistry where you can perform reactions in a flow condition, and you can actually get rid of some of the issues of heat and mass transfer. There is also the advantage of enhanced reproducibility and selectivity of chemical reactions, right? So what I want to show here is that the merging of the two fields, that is flow and electrochemistry, can actually overcome some of the disadvantages you have with batch electrochemistry. All right. Now, the other way you can actually modify 2D materials is using light photochemical processes. Okay. So I want to show you some examples in the literature. One of them is actually Courageux, where you can use a light source to change the phase of molybdenum disulfide. But nevertheless, you can use light to actually trigger a lot of reactions. For example, deoxygenation reaction, or other sort of reactions, light-induced reactions. So it turns out that converting some of these reactions to scalable processes is reasonably simple. And this is an example of continuous flow photochemistry. If we understand these processes well enough, we can actually easily scale up manufacturing or modifying these 2D materials by photoflow chemistry. Now, the advantages here are that it has got a much lower surface area, and you see the light actually pass through very small distance in the tubes and reactors. That means that you have got a much uniform photon flux. So these are the advantages we have in photoflow chemistry. All right, so this is some of our research. My sum is here. So we started to play around with a UV-assisted fabrication of graphene oxide. And this is not something unknown. However, one of the things we were able to discover was that not all UV light are the same. There is certain wavelengths, UVA, UVB, which actually make a more amorphous carbon make defects, whereas UVC, which is here, actually reduces defects, heals pi bonds, and increases the electrical conductivity. All right, we have showed that with electrical measurements as well as Raman spectroscopy data. So this is one of the ways the learnings we had was that the UV radiation could be very specific and tailored for the purpose of modification of materials. From these learnings, Wanqing started to play around and see if we could actually harness this understanding into production and modification of 2D materials. So she found out that at a long wavelength, you can actually irradiate graphene oxide or even graphene, and you can nucleate defects. All right, and then subsequently you can use UVC, a shorter wavelength, and peroxide to actually etch. Okay, and the advantage of this two-stage process is that we can, number one, control the pore size, and number two, control the amount of porosity you have in the holy graphene. I think that's quite an exciting development for us. So what's going on here? Oh yeah, it's dimming out. So initially, Wanqing started to play in batch chemistry. She developed the method. She developed the conditions that which this occur, and then she moved on to a flow chemistry approach where you nucleate and then create the defects. Okay, two-stage process. And I think by now, Wanqing has a method which is fully continuous. Moving from batch to fully continuous mode, she is now able to produce these materials in the lab. Now, oh my God, this isn't a battery probably. All right, there's one more. I'll use the mouse. Just a sec. All right. So the thing which we learned from this work was that in a batch process, we had a production rate of over 27.8 milligram per hour of 50 nanometer holy graphene at a concentration of 10 grams per liter. Whereas when you do the flow process, you can produce about 683 milligram per hour, about 24 times higher production rates. And this happens because we have got an increased photon flux and more uniform radiation, all right, in the flow reactors. And scaling up is relatively easy. You can number up, and if you have 5 reactors in parallel, we can get to about 120 times the production rates. So I guess this is an example of a work where we were able to not only make the material, but also scale up in real quick time. These are examples of various sorts of 2D holy graphene materials. So we can make pores from 8.7 nanometer to 58.2 nanometer by changing the UVA residence time. And then also we can change it by changing the UVC residence time. Correct me if I'm wrong, but the porosity we can vary from about 5% to 60% porosity at different pore sizes. So what it does is it helps us make targeted applications. For example, holey graphene oxide with 5 nanometer pores, we were able to demonstrate its use as a supercapacitor. Pretty good performance compared to what we know. And then recently we learned that about a 20 nanometer holey graphene oxide is really good for carbon dioxide absorption. And then again, about our 60 nanometer pores are ideal for nanofiltration application, where we kind of get rid of smaller molecules. We increase the permeance by a factor of 6. So what we're trying to show here is that a simple approach of photoflow chemistry, you can not only make materials but also scale up rapidly. We are doing some trials with an industry partner in assessing these materials, but I think the promise is great. And then I guess one more example of something which we have been doing in the lab. I know that everybody uses graphene oxide in some form, but it turns out that the purification of graphite oxide is a pretty difficult thing to do. And I'm giving you some examples here. Centrifugation, if you do it in the lab, to 12 to 48 hours, dialysis would take you 5 days. The flow-based method, which PETAR developed, took us 2 to 8 hours. Capital costs are minimal. A carbon footprint is minimal. Scalability is massive. So what he did was, again, this is not graphene oxide, but graphite oxide. It's a particles. So you could have a column where the heavy phase settles below, and then you have convection-driven diffusion, which helps you to purify the material. And you can do it in a continuous flow mode. All right. So this is an area which we are starting to invest a lot, and I think really part of the aim to the activity, especially the flow chemistry approaches. I guess to conclude, graphene-based products are emerging in the market with only 15 years from its discovery. So that's kind of an achievement. If you think about silicon, it took about more than 75 years for it to move from discovery to applications. Now, flow chemistry approaches provide certain advantages in terms of product reliability and homogeneity, lower energy requirements, and cost. I guess this is a great thing for the industry. And the only way industry would be interested is if you can show that there's a cost benefit. I guess a subtle point is reduce uncertainty for scale up, as one of the goals of the hub is to be able to produce these materials in scale. Selected unit processes into the material production and functionalization could benefit from flow chemistry approaches, and it remains a little bit unexplored, but could be a fertile research area. We have shown that electroflow chemistry approaches give you some advantages of the product quality, but scale-up challenges remain to be solved. The photoflow chemistry work Wanqing showed we have advantages in terms of control of nanostructure, and it's quite relatively simple to scale up by numbering. All right. I guess I also wanted to show you some of the recent work from our group so that you get an idea of the things happening in the team. So this is work where we were able to produce very dense graphene oxide electrodes with a very high volumetric energy density. One of the things which we do in our group is make devices. So this is a pouch cell. We fabricate these pouch cells. You will see this a lot in our research papers, because I think one of the ways to convince industry is to make real devices. It's got a very high volumetric energy density, and we were able to power sensor nodes. So essentially a battery-based Internet of Sensor node. A big area of application for supercapacitors is IoT devices. And as I mentioned, Our industry partner has started a joint venture with one of the largest supercapacitor manufacturers in Australia, and we are happy to be part of this project. The other paper which I'm showing here is a membrane. Membrane is a kind of a flagship project in my group. What we did was we started to play around with the chemistry of polyphenols, reacting with graphene oxide, yet maintaining the stability in a dispersion form, and then able to cast membranes, stable membranes of about 50 nanometer thick membranes. So if you make thin membranes out of graphene oxide, it will be very unstable. It will dissolve in water. This type of materials are stable in water. You can run for as many hours as you like. I want to mention here that some of the basis of this technology is being commercialized by a startup right across our, right across the campus. We are producing membrane modules, etc., etc. We can talk about it later on. Another example of our lab is 2D materials for lithium-ion battery applications. Manas did a lot of work on MOT2 kind of material, understanding the mechanisms, using cyclotron studies, etc., etc. And this is the work of Majumder, published a couple of years ago on lithium-sulfur batteries, where we discovered a new way to make cathodes which are expansion tolerant. We changed the microstructure of a traditional cathode to have this bridging bonds. So strong mechanical bonds made of polymers, and what it does is it allows the cathode to expand and contract with a very high sulfur loading. So usually you would have a networking architecture. We engineered the binder to be able to make what is called as a bridging architecture. Our work again published in last year, where we were able to incorporate glucose into the cathode system, which has also catalytic properties, and also modifies the viscosity so that you can make this kind of interesting architectures. We were able to produce these pouch cells. I'm very happy to let you know that in our labs, we are able to produce almost 2 amp hour batteries, and energy densities are about 350 watt hour per kg, which is probably one of the best in the world at this point of time. A bit more research we do on the separator side of lithium-sulfur batteries. This is Petar's work. We functionalize with self-assembled polyelectrolytes, enable lithium ions to go through and reject polysulfides. And then there's also a project ongoing on protecting lithium metals by specialized coatings. Again, a work in which we try to make a membrane for vanadium redox flow batteries, where we, instead of using an Affion membrane, we used a composite membrane made from sulfur-enriched porous aromatic framework and a microporous polymer, and with some interesting properties in terms of anti-aging and charge carrier properties. Our group also has a bit of expertise and interest in soft 2D materials and soft materials. We use a technique called quantitative polarized light microscopy to understand fine structure of colloidal 1 and 2 dimensional materials. These are images of cellulose nanocrystals showing different polymorphism, and we look at this kind of aspects. Acknowledgement is not an acknowledgement of all the work, but acknowledgement for the flow chemistry work. Wanqing Chen, she's here. Maisam did a lot of the UV work. Petar did parts of the work on the cleaning and purification of graphite oxide. Dhanraj was my postdoc who did the electrochemistry work. He's now in India working for National Chemical Laboratories. And 2 of my colleagues from University of Melbourne and CSIRO, who are part of the flow works of CSIRO, they are all part of the new hub. So I guess I'll stop here for questions. Thanks. Yes. Oh, you need the mic, yeah.
Thank you. About the cost, you mentioned, for instance, flow in comparison with centrifusion. Just put dollar sign. Is there any possibility if you tell us some of the numbers per kilogram? Or...
Yeah, I think we have to do the calculations. We have not done the costs. Let me go back. I think this is more a reflection of our thoughts rather than actual calculations. We would love to do those calculations. So, look, capital costs in centrifugation is always high. I would say those equipments are massive, right? Dialysis, you need to use a membrane, replenish the membrane, so I would say not very expensive. The flow-based methods, I'm going to say just a column, right? And you can replicate that. So I would imagine that the capital cost would be pretty low. Running costs, again, centrifugation needs power, right? It's a high-speed process, so you need a lot of energy. Dialysis does not require anything. Well, flow-based, you could use a pump, but the pump is, very cheap pump. So, and I think this is Petra's estimate. I have to ask him how he did the calculations of the footprint. But I'm saying, low energy means lower carbon dioxide footprint. So that is the logic we are using. This is still a work in progress. We have not published it. I thought, we had other papers to get out. This is used by the industry. I think Mainak is using it to clean their graphite oxide material. Yes.
Thank you. Actually, I'm curious about the different reactivity of graphene oxide with UVA, B, and C. Could you comment on that? What is the mechanism behind?
Look, I think this UVA and UVB, I think, are not in resonance with the absorption. I think this is close to the UV absorption peak, I would imagine. So I think that is what activates some of the oxygenated groups, maybe doing a bit of deoxygenation at that point, right? So that creates a defect. Now, the UVC is interesting because it does heal the pi-pi bonds. We saw that. I don't have a full-scale explanation. It could be a photonic coupling reaction. But we see enhanced graphitization happening in these cases. So, look, one of them definitely is a little bit of deoxygenation here. And this is much more enhanced deoxygenation and healing of the bonds. There's a lot of XPS data in this paper that might help us understand a little bit more. But we could see daylight differences when we did the conductivity measurements. When you use UVA, UV, you get nothing actually. It's worse. There's graphene oxide. But when you use a specific wavelength, it increases it quite significantly. Right? Is Maisam here? Anything you want to shed your lights on?
Well, it's a little bit difficult. We did some studies actually on this. We did some studies on this. So you can use visible light to reduce GO, but that is not really a photonic reduction. That's actually a thermal reduction. So GO absorbs the photonic and then transfers to heat, and then that reduces GO. I guess that's what's happening with UVA and UVB as well, but with UVC something else in terms of some other mechanisms that we really couldn't find out. That's really not what we are too much into. But we really saw that, and the first time I got this result, I was like, no, this is an artifact, can't be true. But I repeated this a few different times on a few different substrates. Conductive substrates, non-conductive substrates. The numbers you get is different, but the trend is the same. With UVC, it goes down. UVA and UVB, it goes up.
Yeah. Maybe this is something we can collaborate. I'm going to say we are not chemists, everyone. We are more engineers in our team. So I guess this is something which could be a possible way to think about it. I guess solid-state NMR could be done to elucidate the mechanisms. We'll do this in our lab. We used to do a bit of solid-state NMR when we had a chemist in my team, but we stopped doing it. But happy to collaborate. Alrighty. Any other questions?
Oh, sorry.
Yeah, sure.
Yeah, you showed one reaction to reduce graphene oxide by, using iodine, right? Photo reduction.
Yeah, that is true, actually.
Yeah. So I was just wondering if.
There you go.
Yeah, in this case, you end up with reduced graphene oxide with iodine on the material, or not, making the material more hydrophobic, or?
So what we learned from that was it is not essentially an iodine-doped material. It is iodine clusters on reduced graphene oxide. But the iodine helps in the reduction process because it helps to carry the electrons. Right? It was not really a doped material. We thought we had doped, but all our XPS data tells me that it is not getting into the lattice. It stays there as clusters of iodine atoms, but it improves electrical conductivity dramatically. All right?
Okay, thank you, Mainak. Please thank Mainak again. Thank you very much. In closing, thank you all for your time and attention today. We look forward to the next Talk2D seminar. If anyone has any suggestions for speakers, of course, we would welcome that too. And otherwise, enjoy what is, at least in Melbourne, maybe the last good day. It's not even a good day, but the last good day for a while. Thank you very much, everyone.
Thanks.